Hello, Hari. Good morning.
Hi, Satyendra. Good morning. How are you?
Yeah, fine. Yeah, we are glad to have you as an expert. Thank you for joining.
Thank you
So,
for inviting
yeah,
Satyendra.
so we will be resuming in 5 minutes. We are just
Sure.
waiting for some more participants to join.
Yeah.
Yeah, thank you. Dr. Devesh, shall we start or we should wait for
Of course,
some?
we can start.
Okay. So, I would like to request, our today's expert to start the session. But before that, let me introduce uh, the expert with the participants. So, Mr. Hari is a very good friend of mine, and we have long association starting from NIT Hamipur. So, when he joined as a AmTech there in CFD and heat transfer specialization, after that he joined L&T and then switched to uh, GE. After that, he was uh, working on various problems which are assigned to him related to the thermal engineering and design and optimization of thermal systems there. A part of this, he was visiting engineer to the many countries, more than 20, I can say, and now uh, Mr. Hari has moved to Saudi Arabia, and he's working there in a company. Uh, 1 minute just. So he's now associated with the. Uh, yeah, he's now working as a senior engineer uh, related to the renewable energy solutions there in a division in Alfanar Electric, Saudi Arabia. So now I welcome and would like to request our expert to start with the session. Over to you, Mr. Hari. Mr. Hari, your mic is mute.
Oh, I'm sorry. Yeah.
Yeah,
So I'm
you are
just
audible now.
all right. So is my screen available? I'm just sharing my screen.
Yes, yes, it is visible.
All right. So yeah. Thank you, Mr. introducing me, and hello everyone. Good morning from Saudi Arabia. It's 11 a.m. here, And yeah, I think pretty much Mr. Satyendra told about me, but I'll just quickly go through again, just with some images, visuals. So I started from Larsen and Toubro, worked on a prominent project ITER, International Thermonuclear Experimental Reactor. This is one of the largest tokamak across the globe uh, in the fusion energy era. So it's one of the largest experiment, and around 7 countries are investing in it. I think there was a few seconds of experiment already demonstrated, and further commissioning and experimentations are going on. So it's a long project. I was working on this somewhere in 2015, 16, 17. Uh, so in my journey, I basically developed the cooling towers there. I developed the chillers of like 1100 ton, and the plate heat exchangers of around 30 megawatt sizes. So it was a very large scale and completely a different experience altogether. Then I came to General Electric, and there I had an opportunity to work on the solar inverters. Mostly, when I say the equipment name, I was involved from the thermal perspective. So I was working on managing the temperature and humidity inside the enclosure, also designing the cooling system for the semiconductors, which is the heart of any of the inverter devices, and then went on taking the ownership of the thermal management for the battery systems, the one that you see on the top. I'll come to explain more about what and how, what a scale it is. And then I end up working in Fluence Energy, which is one of known company in the industry. This is one of the competitor to Tesla, a very aggressive, dynamic, and a global culture. Really fortunate to be there, and I learned a lot over there. There, I was not just a thermal engineer; I was owning the complete product. So the image you see on the right top, that's the product. I can call it my baby. I was part of it from the scratch till the delivery. So that's a quick
Mr.
about.
Hari, sorry to interrupt you. If you will be comfortable, then can you please put it on slideshow mode?
It is already
Your
on the
slides are not
slide.
visible to us as a slideshow.
Okay, let me stop and try once again because I was in slides mode.
Your slides were visible to us. We are requesting you to, press the slideshow button so that we can see the complete slides.
Yeah,
There is an option there where 85%, it is written there at the bottom. So there is a one cup kind of shape there, no, at the bottom bar. If you
right.
press that, then
One
there is an
second. I
option
think.
to minimize and maximize the screen, no, at the bottom bar or on your
Yeah,
left
yeah.
corner,
I think
right
I'm not
bottom corner,
much
or
used
right
to
bottom corner.
this interface. One second. Let me try
It's
once
okay. It's
again.
okay. It's okay if you are comfortable like that. There's no problem.
Let me know if my screen is there now. I think it will be easy for me. Is it
Now,
now in the
yeah,
full
it is
presentation?
perfect now.
Good, good. All right. So perfect. Thank you. So going again, like type of batteries. So it will be a very, I would say a casual talk. So in that, I would say batteries, right? It's nothing but everyone knows what's batteries. We have seen a very small cells that goes into the watch, and then now the polymer cells that goes into the phones, and then a lot of batteries, being it torch, being it the EVs, two-wheelers, three-wheelers, four-wheelers, and now it's going at the bigger scale, which is the grid itself, right? The battery energy storage. So a lot of batteries, a lot of chemistries. If we just discuss about that, it would like be a forever session. So what I would just like to tell you is like we had seen these cells small, which goes into a watch, and then the cells which goes into the mobile phones, and then the EVs. Now think of a battery which is of a 20-foot container size. Now 20-foot container means it's a 6 meter wide and 2.5 meter tall and 2.5 meter deep. And then we have many such containers sitting on a site and supporting to a grid. That's where the battery energy storage system comes into the picture. That's the scale of the battery energy storage system. So this tiny cells to that, that's where the battery energy storage industry has gone. And although that's not the only application, or that's not the only use case, but since I have worked mostly on that particular use case, I'm talking, and it is really exciting to see such mega batteries sitting in the site and really doing the charging and discharging. Now, the same thing, like on that note, the very key thing, if we ask why battery energy storage, and then I will link it to the problem statements, and then coming to the opportunities, you can think it from either the learning perspective of what the battery energy storage system is, and also from the perspective that what is the scope in the market. From the carrier, somebody is aspiring to be in this market, then what they should be looking up to. So why ESS? Like wind and sun, they are not always available. It's a very simple thing, though it's not the only use case, but I would start from here. Now they are not always available. So all the renewable energy sources, uh, we have a struggle in this particular place. Okay, in the day you have the sun, but in the night you don't. Wind is not always at the same speed, so you don't have the renewable energy available at the same intensity at all the times. And that is the whole challenge for the renewable industry. And to cater that, the battery energy storage plays a key role. What it does is it it can store all the energy. For example, if I talk about, let's say, a government is planning a big solar power plant. Now that solar power plant would generate excessive energy at the afternoon, but it will generate very low in the nights. So how to fill the gap? Basically, uh, increase the size of the plant, generate as much as you can, depending on the land and then the geography where the plant is. And then whenever there is an excess energy, you put them into the batteries. And now the batteries are there. Whenever there is less energy available, you basically use them. So now this makes it more sustainable and more consistent, so that for all the time we have the energy available, although the nature is not available. So that's the key. But other than that, there are many other applications, including the grid stability. If you read about it, you will find more. Then there is a frequency regulation. So um, if you remember, like, I mean, if you know, like, when the turbine starts or stops, there's a lot of energy required to stabilize them. And similarly, when it stops, it should not be a sudden stop. So in that also, whenever there is a excess energy available, we can put them into the batteries. And whenever there is a low energy, we can basically take from the batteries and support the system, so that the entire process becomes smooth. And likewise on the grid stabilization, there are another use cases where, like in the countries like Europe, and also USA, where the energy trading happens. You might have heard about the stock market and the money trading, right? But there is a huge market for the energy trading, where um, energy is cheap when it is available. It's all about demand and supply, right? A lot of people are generating the power. Many, like Reliance, Tata, people are generating the power. I'm not talking about the Indian scenario much, but you can you can kind of apply the same on the foreign land. So in US and Europe, it happens. Energy prices fluctuates a lot, and what people do, like Reliance and Tata, is they store the energy when it is cheap. When there is a oversupply, they store it into the batteries, and then they use it to generate the revenue when there is a demand and when there is a high prices. So that's another use case where this is being used. And likewise, there are many use cases. Now what it is, that basically it all starts from the cell. So a cell would be similar, like what we use in, let's say, phones, is like 2000 ampere mAh battery, milliampere hour. And then maybe we have that Mi1 10,000, and so on. Here actually the cell uh, rating, let's say the one on the extreme left, its size like around 314 ampere hour. There was a era like 180 and then 280. Now it is 314. Industry is going towards 580 and then even 1000 ampere hour. So once think of, like, what I'm talking about is the comparison from milliampere hour, one we have in the phones, mAh, versus ampere hour, so much larger. uh, and then we use this kind of cells, like one on the left, we use multiples of them, 50s, hundreds, and then we convert them into a block, and then that block is now converted to a complete module where multiple cells, so the one, you can call it cell, it becomes a block, and then multiple blocks put together makes a battery module, in which we have complete system. It has, of course, the cooling. It could be either air cooling, it could be liquid cooling, or it could be a passive cooling. And then there is a lot of sensors to sense the current, voltage, temperature, and monitoring. Everything is there. And then these kind of units are mass produced by the big players in the market, and the people who are actually involved into the grid applications, or the utilities, or the C&I, commercial and industrial applications, or even the EV, they use these blocks, these battery modules, to multiply and make a pack. Is basically a complete like, it's a setup of batteries plus BMS, which is battery management system and intelligence, PCBs, which can monitor and regulate the complete pack functionalities, and ensure that it works safely and as customer requires. And then these kind of multiple packs are put together and then put into the container, and that makes the mega batteries. And that's where actually I work, and it's a huge market. So mostly grid utility. Now I'll while it is just a quick flow about what is a battery energy storage in a very broader term, I'll go specific now to a bit of thermals, and we'll try to deep dive there. And for sure, feel free if anybody has any questions, so you can jump in and we can talk about. So again, in a very broad term, at a very broad level, basically, thermal management's job is to to ensure the safety at first, which is very, everything is around temperatures, right? If you cannot operate something in a safe thermal limits, it will explode, it will burn, right? Batteries are very different species from that aspect. So a very important thing is the safety. Second is the performance. Anything, even a human, right? If you are living in a very hot zone, or you're always stressing your body, keeping it in the extreme weathers, you will not last longer. You will die early. Likewise, the battery. Similarly, if you're not having the air conditioner in the offices, people will not perform well. Their efficiencies will be low. So performance, and then the speed. The same work which a human does in certain time, if they have the comfortable environment around, they have the more favorable circumstances, then they can perform better and they can perform faster. So these are the keys about why the thermal aspect is important for the batteries, to keep them safe. Because if they get into a over temperature zone, they will burn, they will explode. They are actually bombs. You may have seen the fires coming from the two wheelers, right? And they are like a small pack. Hardly, I think they should be um, 1 kilowatt, 2 kilowatt kind of package, right? But when you talk about the ESS industry, battery energy storage industry, these containers are of the size of 5 megawatt hour. I'm not talking about 1 kilowatt, 2 kilowatt. I'm talking about the megawatts, and in that two multiplies. And actually, industry is going towards the 10 megawatt hour. So think of such a huge energy sitting into a small container. It's not a small though; it's quite big. But still, that much of fuel is sitting into one place, concentrated in a concentrated manner. And if there is a fire into one cell, it leads to, of course, burning all the cells. And then if this much fuel burns instantaneously, it can turn out to be an explosion. So thermals plays a key role in actually keeping the battery safe, keeping their temperatures within the safe limits. uh, Although that's, I mean, thermals can alone is not, I mean, thermal alone is not fully sufficient to contain the fire and explosions. There is a lot of factors, the battery quality, the manufacturing, the structure, the chemistry, all that. But thermal has its own role. Then coming to the performance, I'll show you some working Excel sheet also. How does it work? So battery efficiency, when you buy a battery from a supplier or anybody who's making batteries, they have, what they do is they take small cells, they put into the laboratories, and they do the accelerated charging and discharging. And by doing that, uh, they capture the characteristics of the battery cells and understand their life. If I charge and discharge for n number of cycles, how the SOH goes down. SOH is nothing but the state of health. When the battery is full, it's 100% SO. So there are two terms I haven't captured in this PPT, but I would just capture here. SOC is the state of charge and SOH is the state of health. So in batteries, basically, if when you buy a fresh battery, it has, let's say, the energy capacity of 100 kilowatt hour. But over a period of time, its energy capacity starts reducing. Basically, it starts degrading. So the more you operate, more it degrades. Once the energy capacity reduces to 60 to 70%, we call it end of life. Basically, either it can go for recycling or it can go for second life. So basically, you can use it only when it is between 100 to 70% or 60%. It depends on the supplier and the chemistry, and a lot of factors go into it. So what they do, again, I'm coming back, they take the cells, we take the cells, we cycle them, and we understand that, okay, in 5 years, how much is the energy capacity left out? In 10 years, how much? And 15 years, how much? Or in 5,000 cycles, how much? 10,000 cycles, how much? 15,000 cycles, how much? And then we characterize a battery for, if you keep a certain temperature, if you operate this battery in a certain temperature, it would last for certain period. For an example, if you put a battery in a 50-degree environment and you operate it always at 50 degrees C, it might last for only 5 years. If you take the same battery, you might operate it for 30 degrees C for forever, then it might last for 10 years. And if you keep it 25 degrees, it might last for 15 years. So that's how it works. So performance is very closely related to the temperature of the battery that we can maintain. And that is why, again, thermals is very, very important, irrespective of which application. Even if it is phone, or if it is EV, or if it is battery energy storage, if you can keep the batteries cool, they will last longer. Um, of course, so that's related to lifespan. Um, and then coming to the charging speed. So there are, when I talk about speed, right, there are applications. I'll take a typical example of our battery energy storage containers, right? You have the containers now. uh, if you have 100 megawatt hour, either you can or 60 megawatt hour, let me take exactly an hour, right? So 60 megawatt hour, either you can give that 60 megawatt hour in 1 hour, or you can actually dissipate or supply to the customers 30 megawatt for 2 hours. So likewise 20 megawatt for 3 hours, and likewise 10 megawatt for 6 hours. So some applications require really a slow supply, and some applications requires a fast supply, and that's where the speed comes into the picture. So for example, for car, you suddenly give an accelerate, so batteries should be able to discharge at a very faster rate. Whereas if you're supplying it in the homes, and if your battery capacity is enough, you may have to supply it slowly. So when you charge and discharge, the higher the power, the higher the heat generation would be, because it is eventually a conductor. So again, if you want to deliver the speed, like for the EVs, even for the homes, I mean for the utility applications, you are discharging the battery at certain speed. So definitely it is making certain heat. So we have to manage that heat. So safety, performance, lifespan, and then the charging speed, right? So these are the key things where the thermal management plays a role in the battery energy storage. I'll Okay. So now this is about just I captured like why and what is the battery energy storage, why it is, what is the role of thermal management, and now I'm trying to go to capture the some latest trends. So just to show you the industry overview. So this is kind of a utility scale power plant. So you may have seen the power plants where you would mostly see the substation. Like even in India, like in India, it's not that popular yet. Although it is popular, Modi ji has announced some 30 gigawatt hour, and recently I'm hearing even 200 gigawatt hour is the demand of the India, and we have to fulfill that. On that note, one such box is of 5 megawatt hour capacity. So think of how many such boxes industry has to produce to meet 200 gigawatt hour. Even if I go and nominalize that number, even if it is 100 gigawatt hour, you have to produce thousands of them to meet the industry demand and have them available at the grids. So maybe down the line 10 years when you go to the power plants, you may see less of the substation, because substation is just a transformer and the switch gears, and maybe a PCS and all that. But now when you go, you will see every power plant has to have the battery energy storage, and that too it's a major chunk of it. The more the batteries you have, the better you can utilize the power plant. So as I said, India is like 200 gigawatt hour. Likewise, a lot of things are happening in the Europe, even in Saudi Arabia. That's the reason I'm here. And then USA industry is really going crazy. China has already made all the EVs, and their market is kind of saturated. They have deployed like in thousands of gigawatt hour pretty much across the China, and they're already all green. Now they are exporting all across the globe. So there is a huge opportunity in this market. And when I say opportunity, I can further break down specifically from the thermal perspective, that if you have to deliver these many batteries to the market, and there is a mandate across the globe, not the mandate by law, but the mandate by technical requirement, that every grid in the world should have the battery energy storage. Every power plant, every renewable power plant should have the battery energy storage. It's a mandate technically, because it has lot of it adds a lot of value to either be it is utility, or be it the C&I applications, or even small scale industries, or even EV, you call it. Everywhere these components, specifically if battery is required, you would need these components. You need cold plates to keep the batteries cool. Cold plates could also be heat sink if it is air cooled, depending on the form factor and the size of the cell, and what and which application, which chemistry. But there will be a thermal component, mostly a heat sink or cold plate, which will keep the temperature of the cells. Not just a cell. A battery is one aspect, but other than that, you have the other auxiliary components, including the lot of electronics that goes into it, and also the power conversion system. So even transformer, if it has to go, because if you're deploying a battery energy storage system, you have to deploy the respective auxiliary and the DC side infrastructure. So cold plates, then cooling pipes. If you have the battery and if you have the cold plates, you have to supply certain coolant. So cooling pipes, the polyamide pipes, of course you need the walls, sensors, all those things that goes into it. It is needed either by whichsoever. Maybe of course it is not needed for your phone, but in phone also you need some level of heat sink, and not necessarily the cooling pipes. Although there are some cooling pipes which like thermosiphon kind of thing, which is being used. uh, and then comes the chiller, which is nothing but the vapor compression cycle, right? The carrier. the master who has been there ruling the world from very, very long, and it will continue doing so. So vapor compression cycle, nobody can go away with it. A very clean, a very proven solution, which is there, of course, in your homes in terms of the air in the form of air conditioner, and same is there on the cars in terms of maybe coolers, and now on the energy storage as the chiller. Um, then the HVAC, nothing but air conditioner. Controls, again, when you have the thermal components, you might say that controls is not my field, but actually, how you want to regulate these thermals, that all goes with how you want to operate your system. So definitely, you have to have a thermal engineer or somebody, a thermal expert, who has to create the logics that based on so and so temperature and the humidity, I have to operate my equipment this and this way. Eventually, that would be converted into the controls, but the logics and the engineering has to be done by a thermal engineer and give it to the counterpart controls engineer, and then they would develop the codes and all that. But they only understand the codes, and you understand the very core basics of it. So that's very important. And then the venting mechanism. Um, this is again another uh, very critical subject. Actually, as I said, batteries are nothing but they are chalta firta bombs, right? So if you have the 5 MWh, the one that I told about, this container, right? Let me try to just quickly stop my screen. Can everybody hear? Just a confirmation. Hello, hello.
Yes, 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 yes.
Yes, yes, yes.
Okay.
Yes,
You
sir.
want me to adjust my speed? Anything? Let me know. Otherwise, I'll keep going. So let me just quickly play a video, and this is available on YouTube. You can find it pretty much everybody. It's from Sungrow. Sungrow is one of the industry leader in this market. So uh, yeah, I'm just let me just play it. So give me this 2 minutes, and this will give you a brief about how it's a latest trend. So it's a very latest product which is recently launched by a company Sungrow. Likewise, there are at least I can name, if I start naming now, 10 to 20 prominent companies which are working very, very intensively and heavily in this era. And basically that means a lot of opportunity in this industry if you're really an expert, or if you really knows the the stuff, and if you can really convert your theoretical knowledge into the practical engineering that adds a lot of value to the customers, then definitely this is something you should look for. But let me quickly play it. I think it's a very small one, and then we will talk more. Let me just reduce the speed a bit. All right. So that's a cold plate, right? Another cold plate, all the piping, and then that shows cooling and heating using a chiller, which is on the right. And then each battery has like thermal sensors, which are making a thermal map, and we continuously monitor that. So this is showing mechanism about the safety. It starts from the cell and then goes on to the entire container, complete battery system. So every battery continuously measures the temperature, the voltage, current, even the gas particles if there are few gas sensors in the system. So yeah, that's it about the sorry. Can you hear me? Can anybody confirm? Let me stop presenting. So can anybody confirm?
Yeah, yeah,
Yes,
you are
sir.
audible.
All right. So
Yes,
while
sir.
I can take any questions if you have, but basically the battery energy storage industry brings a lot of career opportunities, at the same times provides an opportunity to do a lot of research. In my last 3 years, I was part of doing a lot of work where I was fortunate to be able to make, I mean, be part of 5 patents. So industry is really growing very fast, and what industry needs is a ready-made solution. Like you have seen, everything is in container. Someone can ask why not in the building and all that. So industry needs it fast because, as I said, right, we haven't deployed even few gigawatt hours, and we are talking about India as a country needs 100 or to 200 gigawatt hour. Likewise, if I talk about the Saudi Arabia where I'm currently working, it also has a demand of around 100 plus gigawatt hour, but hardly I think 2 to 3 gigawatt hour is available as of now. And AI, right? When you were doing the images, there was by this AI company by Altman, and it says that okay, our data centers are burning, right? So sorry, our servers are burning. So uh, these data centers are being deployed at a much faster pace, and they consume a lot of energy. Of course, the humans consume the energy, but we are creating more and more applications and more situations which demands more energy, but the energy is not, the energy infrastructure is not progressing with the speed that it needs to be. So while in general, when we are in the engineering college, at least what I have seen and experienced, generally we say okay, automobile and all that, the energy industry doesn't look that great. But when I come here and I see there is a huge opportunities to really innovate and bring the great products to the market, the products which can not just be a product, not just an engineering marvel, but it's beyond that. It should be something that can be quickly fabricated in the factory and then send it to site. Somebody, I mean, people, the governments who earlier were witnessing like a plant execution or power plant building in years, now they give a time of 3 months, 9 months, and within that one has to deploy a gigawatt hour scale project. So market is really catching the speed, and now that's where you would see that industries are really like pushing hard on the people and trying to everybody. If you see any company and they have a culture, speed, competency, so they want great products at the speed. Of course they want products which are made by the competent people and a competent product as a whole, and they want a, in time. So battery energy storage specifically brings a lot of opportunities, specifically thermal for thermal engineers. I didn't talk more about the safety, and also I didn't talk about the CFD. but a lot of computational fluid dynamics is applied for doing this. For cold plate design, people use the computational fluid dynamics, and then they design, they optimize the cold plates, they characterize the cold plates. And for this safety system, although it's more of someone who has done more for someone who has done the fire engineering or an expert on the fire, but still a lot of thermal engineers are involved there in doing the computational fluid dynamic analysis to understand how the overall the safety thing works, like a cell getting punctured and then a gas is coming out, how they accumulate and how the thermals transfer from one cell to another cell, how the packs can burn, and then how those gases together can accumulate, and how much energy actually can come into a container, and at what time it might become an explosion, and what sort of engineering should be done to contain the explosions. So a lot of work even on that side. There is another aspect on the safety side, is um, to to basically regulate the concentration of the fuel. Basically, there is a lowest flammability limit. So LFL, right? So when the gases emit from the cells and comes into the enclosure, if the gases have the enough concentration that it can reach its LFL limit, then they will catch the fire, and then they will start burning. So a lot of engineering happens around controlling the gas concentration, such that we can keep the concentration below LFL, so that the ignition and of course the explosion can be avoided. And for that, again, the ventilation comes into the picture, that in such situations, how much ventilation you should have and how the ventilation should happen, from which areas the air or the fresh air should come in, so that it can effectively take along the gases and exhaust it out, so that a system would not burn. Likewise, when even if a system is burning, uh, there is how on, like, the wind velocity and then the intensity of fire propagation, again that goes into the CFD, and people decide that what should be the distance between equipment to equipment, so that not just the enclosure or not just one equipment is burning, rather the entire power plant might burn, right? So there are certain regulations which people follow and adhere to, and design these systems. um, Other than that, like when you see, like I saw in a big power plant where hundreds of equipments are sitting, and all of them are emitting the heat in 60 kilowatt, 80 kilowatt, 100 kilowatt capacity, and think of hundreds of such equipments are emitting that much heat, and that heat is getting into the environment, and it is highly likely that the heat coming from one equipment might affect the cooling of another equipment. So again, the computational fluid dynamics is applied, and a plant level short circuit analysis is being done, and we assess that, okay, what is the optimum spacing between the equipments in all around, so that we can have a efficient plant and not run into problems in the future. So that's another aspect where thermals applies. um, so yeah, that was the brief about the battery energy storage system. If you have any questions, I can take, or otherwise I'll walk you through the Excel sheet that I have. No questions?
Participants, any query? Okay, then, sir, we can move, I think.
All right, sure. So let me share my screen again. So from the thermal engineer perspective again, right? I mean, although I can talk about the complete product because I own that, but uh, for this audience, um, this is what happens in the battery energy storage. So, a lot of variables. I'll just walk one by one. So this is a working Excel sheet which I generally use to design the battery energy storage thermals. So it starts from I look at variables, right? The altitude, really, as the altitude as we go higher, the density of the air reduces, and thereby effectiveness of thermal systems reduces, because the air doesn't have that many cool particles in the same volume, and that's why we need more air. Or if the same system is being used, that means it will be less effective in terms of cooling. Then um, of course, what kind of equipments we are using, what tonnage we have, um, what are all components are there into the system, we take that. And then what life of the battery that we are targeting to address, and then what temperature we want to keep it at. And then of course, while in India mostly, I mean, we do see the summer and winter, but if you go Canada and if you go some regions of America, even the colder climates are very very harsh. So we need to have, while we equally bother while we bother a lot about the cooling, in those regions we have to also keep the temperatures minimum enough that batteries continue performing and doesn't go into the dead stage. So we need heaters as well. So a typical thermal engineer would gather all these inputs from uh, the, of course, the colleagues in the industry, from the team, also define each and every component. And then these batteries, especially for the battery energy storage, the more populars are like 2 hour and 4 hour and even 8 hour. So when I say 2 hour, 4 hour, 8 hour, what I mean is, as I said, if I have a 5 megawatt hour equipment deployed at site, and uh, we might be dealing with an application where when there is no power, customer actually needs consistent 2.5 megawatt power for 2 hours. So I call it 2 hour application. um, so basically we have to run the equipment for 2 hours continuously, discharging and supplying to the customer the electricity. If it is 4 hour, that means of course it has to do 4 hours. Now the same 5 megawatt hour would not do 2.5, it would do even half half of 2.5, right? 1.25 megawatt to the customer for 4 hours. And likewise there are 8 hour applications. So generally when you read more about it, it goes, people call it with the hourly application. And then if it is 2 hour application, simply I know the power, that much power I have to flow through the equipments, and for that power what the current will go through the conductors, basically cells, and how much heat it would generate. That can be calculated using simple formula I square R. Although it's not that simple, there are some characterizations that happens. So we use that, and this model particularly shows that, okay, how my ambient is regulating. Okay, all right. So for this given ambient profile, which is somewhere starts from 40, goes to somewhere 35, and then sometimes 50 degrees C also, and then goes down. So uh, that's the temperature for that kind of ambient temperature. If I have to deliver 2 cycles, when I say 2 cycles, or here it shows 4 cycles. So the battery temperature starts rising when we are charging. So basically this yellow line here is says when it goes up, basically it's charging. When it goes down, it's discharging. And when it is flat, it's basically rest period. So it's a typical profile of any battery energy storage. And this is why I'm coming to all this, because thermals of the battery energy storage is bit different than any other application. We talk about air conditioner sizing of a room. You just calculate the number of persons, number of heating components, and then you calculate all the heat, and then you say, okay, to dissipate that much heat, I need so and so tonnage of the air conditioner. If you cool the semiconductors or any such electrical heating devices, you just need a number that, okay, I have X kilowatt being generated and I have to dissipate that. How effectively is definitely a question which all goes with the effectiveness of cold plate or the heat sink, and then how much flow you have, all that parameters comes. But in those applications, you just need that total heat generation number, and that's it. That gives you a ability to define your cooling capacity. But in battery energy storage, it is a bit different. In battery energy storage, the capacitance plays a key role, and that is why it's not instantaneous. The time constant is not zero, like your semiconductors or any other heating or cooling applications. Here, your batteries are huge mass. Just to give an example, this complete battery 5 megawatt hour that I talked about is 42 ton in the weight, 42,000 kgs. Think of it. That much of mass is available. So even though you don't use even though batteries might require, let's say, 100 kilowatt of cooling, but actually you can keep them cool just with 30 kilowatt, one third of it or one fourth of it. Why? By using the thermal mass of the system, meaning when the heat is being generated, you can't, you don't dissipate all the heat, and you can't dissipate all the heat because of its own inertia. System has inertia, meaning there is a heat generation into the cell. That heat comes to its periphery, and then from periphery it goes to the sink or the cold plate, and from there it dissipates to the coolant, and then coolant takes the heat away. So there is a path that heat has to follow, and in that path there is a thermal resistance, and because of that you cannot dissipate all the heat from any cell instantaneously. You also need delta, enough delta. Cells should reach to enough temperature to give you enough room to actually be able to extract that heat and take it out. So for those reasons, you don't take all the heat instantaneously out, and you can't. And that is the reason one has to look at very holistically. That means one has to put all the parameters, the characterizations of the cell, characterization of the cold plate, characterization of the plumbing, characterization of the cooling equipment, put together in a closed loop, and also relate that to the environment, so that we have a judgment of how much heat at a certain time is coming. For example, this is like a 16 to like 28 hours of window, right? In that 28 hours of window, even though the heat, I mean, cell heat generation was kind of same from where it starts till where it ends. But if you see, the cell temperature profile is not same, because uh, you cannot dissipate all the heat. Had you been able to dissipate all the heat, we could have maintained the cell temperature constant. But as we charge, and we give a bit of rest, you see here. So we start charging, it goes charging. So during charging, slowly we are extracting a part of the heat, and remainder is actually being stored into the capacitance that is available, which is battery itself, and that's why it is cooking, its temperature is rising. When we give a rest, now cooling equipment is still running, and it is taking out the heat whatever it can, and that's why the cell temperature is going down. Further, when we start discharging, which is this yellow line, the cell temperature I mean further start rising. It doesn't mean the cooling is not happening. Cooling is happening, but not all the heat can be extracted. So it keeps rising, and then again there is a rest period. It keeps rising and rest period. So what happens is, the criteria to design the cooling system here is, um, the supplier, basically the manufacturer of the cell, would provide you a certain threshold. In this case, threshold is this green line. So you have to always maintain the peak temperature uh, below this particular threshold, and if you are keeping it below, uh, manufacturer is able to guarantee you the performance of the cell. The performance means the speed as well, charging discharging speed, if in this case it's a 0.5 c. uh, Also the life, 20 years of life or 25 years of life, whatever they claim based on their own research, that they can, that remains to be valid. If we go above this limit, then warranties would be void. We would be penalized. Basically, our battery would last not last as much as they have claimed, and of course we will not be able to claim the warranty. So uh, that is how in general a thermal dashboard of energy system looks like. In this case, it's basically two full cycles. You see the charge, rest, discharge, rest, charge, rest, discharge. So one charge discharge is one complete cycle. So here in this case, two cycles are there. So this particular use case is for a customer who is asking two cycles and allowing some rest between the charge discharge as well as between the cycles. There may be a customer who really don't have that room, and he may say, okay, no, I need a battery system which should last just one cycle maybe, but I don't have an ability to give a rest. I need back to back charge and discharge. Or maybe a customer who might ask even multiple cycles without any rest. In that case, they may be okay to accept lesser life, or maybe they're okay to accept the bigger footprint. Footprint is really a big question, and that is why everything is becoming compact, 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 and hence thermals also becomes challenging. So yeah, in nutshell, there are different customers who has different requirements, and thermal engineer plays a key role. You think of batteries are actually electrical component, but a thermal engineer plays a key role in defining and saying on a catalog, on a data sheet, that what my product is capable of, what we can do. And that can be done with this people call it complex, but for thermal engineers it may not be that complex. We definitely need to put the equations in a transient flow, connect all the variables, and then uh, run the cases and assess for given application where we would stand. So, and then batteries doesn't always generate the same heat, while they would generate a different, I mean, less heat when they're new. As they grow older, their heat generation starts rising. So when we look into the design, basically we will have to always design as for the worst conditions. uh, so we keep in mind what will happen at the end of the life, what will happen in the 50 degree C ambient, what will happen when there is a raining around, what will happen if it is around a seashore where even salinity is a factor which can corrode or erode the thermal components. So all those factors we keep in mind, and then we, of course, on paper, theoretically, when we design and do this, we do also uh, be careful not just about the thermal analytical part, but also about what material is going into the cooling system that we are designing, or we are buying it from somebody else. So we have to have the right specification in place, so that we buy the right equipment and supply to our customers. So yeah, basically, this profile then would be fed. Basically, this temperature profile would be fed again to some data science, data analytics people, who would try to, because you see, one cannot say that a very complex piece, right? So this green line is a threshold which a supplier has given, somebody has given. Forget about supplier. Some technical person who has done the cycling of this cell and has calculated certain life, that if this cell is operated at 30 degrees C or 40 degrees C, I can guarantee 20,000 cycles. But in reality, you see, cell, even for a cycle, even for half cycle, cell is not sitting at one constant temperature. That means temperature is continuously going up and down. And then there could be an average. Maybe there could be an hourly average, but definitely there is an average. Not all, I mean, if we consider the peak only, and if we adhere to it, we might be over designing the system, right? So supplier has said, okay, I need 35, and we are following 35. But honestly, sometimes we are actually at 22, 23. Very rarely we are touching 35. But uh, but manufacturer has tested their cells for 35 degrees C, and that's where they're giving the life. That means there is a lot of buffer if you're always operating this system at a lower than threshold. So that means we can use that buffer to compensate sometimes when there is a peak summer, 50 degrees C environment, or maybe at the end of the life, the last 1 year of the complete life cycle. We can compensate a bit if we have more intelligence to understand that if I operate these cells below 35 degrees C, or in a daily basis, if my average temperature of the cells differs, on an aggregated basis, what should be my life cycle projections? So that's where this data analytics and data science and the people comes into the picture. We give them the data from our analytical calculations, that these are our average profiles for cold environment, maybe for first 3 months, next 3 months bit warm, then very hot, and maybe very cold. And then they take into the consideration, they also consider the characterization of the cell for the life cycle, and then they use all this data to make some sense of, okay, how much more buffer we have, how much more we can deliver to a customer, or how much less. And that is how people really um, really play in the market. Those who really have a good data science skill and thermal skills, of course, they even play better, basically, just by doing the data science, right? Not doing much of the designing, the manufacturing, and all that. Just by doing the data science, they are able to say that no, we will not offer only 15 years, we will offer 17 years. So think of 5 companies are competing. A company has certain skills which has thermal and data science and maybe a bit of electrical, and then they are able to say to a customer that while everybody else is offering you 15 years with the same cell, I can warranty or guarantee you for 17 years. So they win. They make a competitive edge, and they offer a better product, and convince to a customer with fact, with the data, that we are better than the other competitors. So that's how the skills plays the role. So while I kept talking about the thermals, if you have something from the data science or the analytical side, if you are very good at the analyticals, then you might go even further and higher. So I think if I keep talking, it might be complete day. So I would like to stop here and would like to understand from everybody that if you have any questions, I can answer, or we can have some very casual discussions about any silly question also. That's fine. Go ahead.
Dear participants, if somebody would like to interact. Mr. Hari, I think there is no question.
Okay.
So, Dr. Devesh, I would like to request you to, to conclude the session.
Hello, am I audible?
Yes, you are audible, Dr. Devesh.
So any query from
Hari,
participants?
Dr. Devesh is also coordinator of this short-term course, and he's a faculty in the Department of Mechanical Engineering. And our chairman, Dr. Rajiv Kukreja, is also has also joined the session. Who is
Yeah,
associate professor in that government.
Hi.
Hello, sir.
Hi, sir. Good to be here. So I think I would just, what I would say is to audiences, I'm not sure, like maybe I was too clear that nobody has any questions, or maybe I was too boring that nobody understood what I was saying.
No.
So
In fact, your lecture has been very very useful, because everything you talked only from the industry point of view, practical point of view. That was
yeah.
quite, that is commendable, sir. This was really, and maybe the participants who are they have started this kind of thinking. Or you also told very detailed thing about the data analytics, which is very much applicable in your area. And many students are working in the data analytics. I'm mechanical
Yeah.
engineering student, so really your lecture has been very very good. Maybe it will take some time to absorb the thing, because you have touched so many
Yeah.
points. Actually. Yeah.
Yes.
Thank you so much
That
for.
is actually the pure application, in the industry. I think.
Yeah. It's a pure
So what
experience.
we do here, it's the teaching and the theoretical part actually. But
Yeah.
what you have discussed, it's actually and especially I
Dr.
think
Sundar,
the Excel.
I think
Excel.
you have the details from Mr. Hari Ram, so that
Yes, sir.
if you like, we can contact him in future.
Yeah, sure.
Sure.
Yeah. That's great.
Because here many work is going on in the battery.
Yeah.
Yeah.
So if any query from the participant sides, as sir said, any silly questions also will be welcome. So if you have any query,
Dr. Devesh, your
otherwise
voice
we
is
will.
low.
Am I audible? No.
Yeah.
Yeah, you are audible, but your voice is low.
Oh. Let me
Okay, it's
check.
fine.
Now am I audible?
Yeah, you are audible.
Okay.
I think
So
if you speak a little bit louder, then I think it will be fine.
okay. So now if you have no query, okay, no query from participants end, then we will move for the valedictory sessions.
Yes, yes.
So here we are waiting for the our HOD sir. So let's join him and then we will start the valedictory session. Let me contact. Okay, I will inform him.
Okay, so before the valedictory session, I would like to, you know, thank to the today's expert, Mr. Hari Patel. So we are glad to have you as an industrial expert for today's lecture. I think it will be now, I think about 10 there in the Saudi Arabia.
Actually, it's a 12, and that's where I messed up. I'm sorry. It's a 12
Okay.
now. I calculated it the other way around.
Okay, it's fine. It's fine. So we are great and delighted to have you as an expert, and it was a wonderful lecture. And we also recorded it, and with your permission, we'd like to share that recording to the audience as well.
Sure. Yeah.
Yeah. And we are also streaming the same lecture live on YouTube. So that is our own channel. So there we also keeping it for the reference of the participants.
Yep.
So Hari, okay. So we will be great when you will be coming, when you will be visiting India. Please let us know so that we can invite you at NIT Jalandhar as well as our chairman for this STC and Dr. Rajiv Kukreja said. So it will be great to our students also to have the flavor of the industries, what industries are working on the latest, technology, which is latest and highly, propping technology, which is battery technology at present.
I think
No, for sure, that will be an honor for
HOD
me.
sir has
Thank you.
joined us. So we can proceed
Sorry?
for the valedictory. Dr. Satin?
Yeah.
Okay. It's good afternoon. So good afternoon to all of you. Now respected other faculty members and of course the today's expert, Hariharan Patel sir, and my dear participants. It's my immense pleasure and privilege to deliver this valedictory address for this enriching the short-term course, okay, on the design and optimization of thermal systems. Over the past few days, we have all come together in the spirit of learning and collaborations and the innovative ideas through the different lectures. And today we have arrived at the concluding remarks. And definitely we celebrate the knowledge we shared, which we have gained here, and the connections built here actually. Uh, Here, thermal systems are at the heart of the energy, energy conversions, efficiency, the sustainability from power plants, refrigeration systems to different automotive engines and renewable energy solutions also. Through the different expert lectures, hand-on sessions, and active discussions, this course has offered an understanding of the theory and the applications. I think today we have seen the practical applications, okay, of the battery. So applications of thermal and the system optimizations. Okay. So now with this, I would like to call our HOD sir to please put their view here, okay, on this valedictory session.
Thank you, Dr. Devesh. Sri Hariram Patel, BESS, Saudi Arabia, Chairman Dr. Rajiv Kukreja, and Professor Subhash Chandra, Conveners of the short-term course, Dr. S.S. Sandhu and Dr. Ranjan Chauhan. Coordinators, Dr. Satyendra Singh and Dr. Divesh K. Singh. Distinguished speakers, esteemed faculty members, participants, scholars, one and all. A very good afternoon to all. It gives me an immense pleasure to welcome you all for this valedictory program on short-term course on design and optimization of thermal systems, an experimental and computational approach organized by Department of Mechanical Engineering, Dr. B.R. Ambedkar, National Institute of Technology, Jalandhar. On behalf of organizing committee and department, I extend my heartfelt gratitude to each one of you for your participation and presence. I also handled the course Design and Thermal System for the master's students. I understood the significance of this course, which is more relevant to the industrial expectations. And also, this course is more associated with the skill development such as CFD, MATLAB, AI, and machine learning, and so on. I hope all the participants gained more knowledge as well as hands-on experience to develop their domain expertise in the field of thermal systems. Learning a new course offers numerous advantages of including that's career advancements and cognitive function, increased confidence, and personal enrichment. It can also improve your problem solving skills, boost creativity, and help you to adapt to new solutions and challenges. In 2018, I want to share one of my experience to learn this course, like through the short-term course or this learning the courses to the teaching learning process. In Tamil Nadu, timetable coordinator offered me a new course that time. Solar energy is a new course that time for me, 2018. That time I hesitated to handle this course as I'm not aware of that course completely, but I have no options. I took that course and I learned the course, enjoyed it, and later I got the 4 funded projects in solar energy and granted patents for each and every idea of that project. Why I'm quoting this example is this type of short-term course definitely ignites your learning and understanding capacity and enrich your skills, especially for the technological development that will boost you not only in your career, in the problem development, product development, etc. I request all the participants to learn new technologies and courses without any hesitate or the fear and break your comfort zone. I wish to congratulate all the organizing team, especially that Dr. Satyendra Singh and Dr. Divesh K. Singh for their dedicated planning and execution. I congratulate all the participants for your wholehearted support and participation. We are extremely privileged to have distinguished experts from academia, industry, and abroad, especially from USA, Norway, France, and Saudi Arabia, who shared their invaluable knowledge and experience. I would like to extend my heartfelt gratitude to them for accepting our invitation and sharing their expertise. We thank all the administrative support from the NIT Jalandhar. Thank you, and I wish you all the best for your future achievements. Thank you. That Divesh, you can proceed.
Yes, sir. Am I audible, sir?
Yes, 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 yes.
Okay, with this, I would like to take the moment to thank our resource persons, the guest speakers who generously share their time, their experience, and their insight knowledges with the different lectures. Their sessions have sparks of curiosity, and definitely this will expand our perspective in the different remarkable ways. Uh, Now, with this, I'd like to thank our other organizing teams and the other coordinators and who seamlessly planning and schedulings and supporting behind the scenes actually. and that ensured the success of this course. And I would like to thanks to all the participants, your enthusiasm and the thoughtful questions and eagerness to learn that created an engaging atmosphere for us. I hope that you will carry will carry the lessons which you have got from this short-term course here forward in your respective fields, and will apply this knowledge in the different research fields and in the different in your different careers. Uh, I want to thanks our research scholar also who was actively involved in this course. I would like to thank the HOD sir, our head of the department, mechanical engineering department, who has always been the backbone of this short-term course. And I would like to thank our worthy director sir for providing this opportunity to organize this short-term course and provided us all the supports which required for this short-term course. Uh, Let us not consider this as a hint, but rather one of the milestones which we have covered. Because in the future we will plan such types of short-term course with other upgraded topics like machine learning and AI. May this course will act as a catalyst, for the further explorations of the research and the innovative ideas. Uh, Now, here along with this short-term course, I have actually shared conference details in the chat box. So I request all the participants to please go through that chat box. Uh, it means this is the conference which we have planned to organize in the January month of the next year, which is for the date is 16th to 18th Jan of 2026. In this conference, we have the four track actually, that is the thermal, the fluid, green energy, and we have included the emerging areas, and that's why we have given the theme and the title of this conference, that is the International Conference on Thermofluids and Green Energy Technology. So we have the four tracks, that is thermal, fluid, green energy technology, and there is another track which includes some other the recent emerging areas. So I request all the participants to please go through that conference websites, and if you are working in any areas of that tracks or the subject areas, you can submit your papers. We are planning to generate some, or to get the approval from the publisher so that we will publish our the conference papers there. So we are actively involved in this conference. Okay, we are in the touch of the some publishers. So let's hope that we will soon we will get some positive result from the publishers. And as soon as we will get that approvals or any response, we will inform through that conference. So I request you kindly go through that conference website, and I also request to give a wide publicity of this conference so that we can again make this conference success as we did for this short-term course. Now, with this, once again, thank you all for making this program a success. Wishing everyone the very best in their professional and the academic journeys. Okay. Thank you all. So this is all from my side. If Dr. Satyajit want to say something, then he can proceed.
Yeah, I also would like to thank all the participants and today's expert, Hari, for joining our valedictory session as well. And I hope that in the future, when we'll organize the such events, so we'll invite all the participants, and we hope that they will join. And also, as you briefed about our upcoming conference, so we hope that the participants they will send their such publications, manuscripts, and share their research with us as well. So with
Dr.
that, I
Sundar,
also
Dr.
thank
Sundar,
all the.
can we have the feedback also from some of the participants if they want to have?
Sorry, sir.
Can we have a
Feedback.
feedback
Yes,
at least from one or two participants? I mean,
Yeah,
if it is
sure.
possible.
Yeah, of course. So, as Professor said, I would like to request participants if they want to, give their feedback or they would like to share their view about the short-term course.
Good morning, everyone. Am I audible?
Yes,
Yes,
perfect.
Rahul, you are audible.
So I'm Dr. Rahul Agrawal. Basically, I'm from the Spain.
Okay.
And it was a very nice sessions, interactive sessions, and basically it is the need of the hour
Mhm.
of this thermal energy storage and the thermal energy. So
Okay.
all the sessions are very nice, and the main thing that I am not able to attend the first half properly because of the time difference. But I attended all the sessions second half. That is basically on the hands-on training,
Mhm.
and all the sessions are very good, very planned. Everything was very good. Thank you so much for
Thank
this
you.
opportunity.
Thank you. But you always have these lectures available to you on YouTube. You can,
So, yeah,
yeah,
yes, sir. I will definitely. I will go.
yeah.
So,
Any
thank you.
other participants who would like to give their view? Any other participants? I request participants, please give some feedback from your side.
ठीक है, Dr. Divesh, you can conclude.
Okay. Now with this one, there is one announcement that we will share a Google form, okay, for the collection of the details, because the earlier details which we have taken, and there's just some error in the, I think, the college or university's name actually. So we will again send a Google form so that we can prepare the certificate accordingly, so that there should not be any mistake. So we will circulate a Google form. I request all the participants, please fill that Google form as soon as possible so that we can release the certificates. Another guidelines also will be shared if there will be any. So thank you all. Thank you all for this short term.